Hello, hello. We are on part 3 of this Unit 10 on solids and liquids, the condensed phases. And so we've already talked about liquids and the different intermolecular forces that hold them together, as well as some of their properties like surface tension and viscosity. So now we're going to look at, well, what if you cool these liquids down so much that eventually the particles are overcome by these weak intermolecular forces and they come to a stop, they come to rest, and the particles get locked in place. That's what you have in a solid. So it's not that there's absolutely no motion, but there's no translational motion. So each of these particles is stuck adjacent its neighbors, and it's not able to move about freely like it could in a liquid. So there's generally two main types of solids. There is crystalline, and then there is amorphous. Now, crystalline is going to be the one we're more interested in this chapter because it's a little bit more repeatable, and it's what you get when you have long range order. Again, that word crystal isn't in crystalline. Again, if you think of crystals like diamonds and rubies and sapphires, they're normally transparent, they're shiny, and those are some of the property. The reason they have those properties is because there's the atoms or molecules or whatever that's making up that thing is in a highly repeated network. So they're rigid and they have long range order. That's key. So you can look at a tiny section and know that it's going to repeat over and over and over and over and over. And they're generally pretty stable because they've achieved the maximum amount of bonding. So the best configurations of intermolecular forces where they've been locked in. Now, in contrast to crystalline, there is amorphous. Now, that A prefix A is kind of like without, and morph is in shape. So amorphous does not have long range order, it lacks it. And so if you look at one section here, it's not going to be identical throughout. Now, if you were cooling down a liquid to a solid and you do it gradually, you're pretty much giving the atoms and particles enough time to find these optimal arrangements. It's like if I told you, hey, first day of class, I'm going to give you 5 minutes to work out your own seating chart, and you can position yourself where you want to be in the class. You can make sure you're sitting next to all your friends and you're sitting far away from your nemesis or frenemies. But imagine, and so you'd end up at these optimal placements. But imagine what if you came into class the first day and I said, I'm going to give you 10 seconds to get a seat. And I said, go. Well, then there's this mad scrambling to just get a desk, a chair, and you're more likely to end up with an amorphous configuration where you didn't want to sit next to Becky, but now you're stuck next to Becky all year long. And it was just because there wasn't enough time to find optimal positions. That's what happens. That's what you happen, or how you get amorphous. It generally occurs when freezing is rapid. So you don't give the particles a fast enough time to move around, and they just get stuck. So if you quench a liquid, you end up, or just in any way you're cooling it rapidly past the freezing point, you get this amorphous solid. There's not enough time to get the optimal position. So by saying this is amorphous, there's not a whole lot we can, strategically talk about, because by definition it's kind of random. So we're going to talk more about crystalline because there's a whole lot of different things that can vary. So like we could talk about carbon. So two very different properties of carbon are diamond versus graphite. So you change the repeating pattern and you change the properties. Where charcoal is amorphous carbon, it doesn't have a nice repeating pattern. Again, when you hear that word crystalline, again, you think of crystal, and so gemstones. Here's a bunch of different gemstones and some of the chemistry behind them, from pearls to opals, aquamarine emeralds, topaz, rubies, sapphires, diamonds, and so there's a lot of information on this slide you could look at. Orange box, you don't have to memorize anything, but again, what they all have in common is a general, they're all translucent, like light can pass through them because they have this highly ordered pattern. and it could be from silicon and oxygen, or sodium aluminum silicates, or carbon or aluminum oxides. And so the different elements give them different properties, but they all have a crystalline structure. Now, probably the most frequently seen amorphous solid is glass. So take silica oxide and heat it up till it's molten, and then quench it. So cool it down quickly, you'll end up with an amorphous solid. Again, it's kind of evident that when you apply pressure to glass and it breaks, you get all of these irregular shapes, these pattern, these there's no set pattern that emerges. Where if you were to again if you were to study diamond cutters, because of the crystalline nature of a diamond or any of these, you can cut them into very precise geometries, different shapes, because when you can apply, they know that when you apply pressure at certain points, it'll cut in a very specific way, but not glass, not amorphous solids. This is when we would be watching this video. You should watch it on the Prince Rupert's drop. I'd also make one. All you have to do is pretty much heat up a piece of molten glass and allow it to drop into water, and it'll look like a little rain droplet. It's why it's called Prince Rupert's drop, and it has some really neat physics behind it. Because if you take a pair of pliers and try to squeeze the droplet on the largest part, it won't break. It becomes very, very strong, but it'll have a tail. And if you just barely snip the tail, the thing will explode into just a million pieces. And this video shows it in high speed and talks about it. It's pretty neat. You should watch it. Now, what all crystalline substances have in common is a repeating pattern that we call a unit cell. So this is just a generic unit cell, but it forms a crystal lattice. We've heard that term before. We know ionic compounds form a crystal lattice, but other substances can too. Just ionic compounds always form a crystal lattice. So here's the unit cell, and it has a lattice point. So depending on what type of substance we're talking about, this could be an atom, it could be a whole molecule, it could be an ion. And the red lines are intermolecular forces, ionic bonds, metallic bonds, covalent bonds, some type of attractive interaction between the lattice points. And then this can repeat over and over and over and over and over. Now, there's a number of different types of unit cells. These are the main 7. The simplest is called a simple cubic unit cell, where the lengths on all directions are equal. The angles are all 90 degrees, and so something like table salt has this, but when you start looking at other where tetragonal has one longer side than the other two, or orthorhombic where none of the lengths are the same, or rhombohedral or monoclinic where not all the angles are 90 degrees. Triclinic, hexagonal. So most solids, when they crystallize, they will adopt one of these configurations. There's a few others in subcategories, but I put an orange box around this because it's besides knowing that different unit cells exist, you don't have to know the different types, because there's a lot. But you could look up pretty much, if you're looking up properties for any solid substance, you could look up crystal structure and see that it would adopt one of these main 7. Now, besides the unit cell, and then the thing I do want you to know about unit cells is the type of unit cell can sometimes drive the properties as well. So water adopts a hexagonal structure seen here. And so you can roughly see this hexagonal shape with all the red dotted lines representing hydrogen bonds. But it helps explain why water has that weird quirk of becoming less dense as a solid. So at 4 degrees Celsius, where it has its maximum density, this hexagon is, you could almost think of like a box that it's loose enough that there's still an extra water molecule that can fit inside this. However, when it cools down to the freezing point, when it goes down to 0 and it becomes more rigid, the water a water molecule that was inside this hexagon essentially gets popped out. And that is, since now it's more like an empty box and that water molecule has to go somewhere, it's taking up more space. Again, because a empty box is less dense than a box that has something in it. We also see that when we look at snowflakes, and here's a nice link that talks briefly about it. Again, snowflakes, you typically see these six-sided hexagons, and that's because fundamentally from the molecular level, it adopts these hexagons, and that is what manifests when you have millions and billions and trillions of water molecules all crystallizing on top of each other. Another factor that can come into play is packing. So again, there's going to be a bunch of different types. Simple cubic is where you have, there's 8 all forming like the corners of a box, but then there's body centered where there's another one packed in the middle, and there's face centered where this one's a little bit harder to see here, but pretty much, again, think of simple cubic. There's 8 on all the corners, but then face centered means there's one in the front, top, bottom, left, and right, and behind it as well. And so really this mainly affects the density. So something that is face centered can pack, again, more tightly, more efficiently, and will be more dense than something that's just simple cubic. But again, you don't have to know the different types. Again, other examples, table salt. If you look under a microscope, it looks like tiny cubes. And if you pulverize those tiny cubes, it looks like even tinier cubes. That's because down to the crystal lattice, down to the unit, the formula unit, sodium and chloride always adopt the same configuration. All 90 degrees, distances between sodium chloride always identical. Quartz, on the other hand, grows hexagonally, just like water. And so its crystals, when you allow them to grow, you can see these hexagons, again, coming about. Now, we might say these things grow simple cubic or hexagonally, but most things are polymorphous in that they don't necessarily have to have just one unit cell. It more depends on the crystallization condition. So things like temperature and pressure. How quickly was this done at high temp, low temps, low pressures, high pressures? And so you might look at these two crystals and they look completely different, but they're both calcium carbonate. And the difference is one crystallized to be orthorhombic and the other crystallized to be rhombohedral. I like this one because I think it looks like a transformer. But calcite and aragonite are both minerals that are exactly the same thing, calcium carbonate. Now, where polymorphous can refer to any substance, if we want to talk specifically about one element, we use the term allotrope. So there are various forms of the same pure element. Phosphorus, there's 4 main allotropes: white phosphorus, red phosphorus, violet phosphorus, black phosphorus, and their properties change even though they're technically all the same element. Where red phosphorus is used on matchboxes, white phosphorus used to be used in incendiary ammunition. So essentially grenades that would rain down fire. So instead of an explosion, white phosphorus ignites at like 30 degrees Celsius, which is pretty unfriendly. There's a number of different sulfur allotropes where sometimes it's octocyclic rings, sometimes it's hexacyclic. We did a Fire Friday where we melted sulfur and then we poured it into water and we ended up with plastic sulfur. So their properties change as the arrangements change. The element with the greatest number of allotropes is carbon. Again, going back to its versatility, there is a almost limitless number of ways carbon can arrange itself, from diamonds to graphite. Carbon nanotubes have become a huge boost in technology the last couple of decades. This is a buckyball. It looks like a soccer ball where there's 60 carbons, and they do occur naturally. They've been detected in things like just smoke and other things. But all of these, they're allotropes. So to end today, we're going to look at 4 main categories of ionic crystals. The first is the ionic crystal, and this is the one we've talked about the most because ionic compounds that we pretty much always exist in a crystal lattice with a unit cell. And so here we know it's always going to have a metal with a nonmetal, cesium and chloride, zinc and sulfur, calcium and fluoride. And then here we're seeing their different unit cells represented. Again, when we look at the formulas, 1 to 1, 1 to 1, 1 to 2, remember, those only tell us the base ratio. So if you look at this unit cell, it looks like there's 6 times as many cesiums as there are chlorines. But as this thing repeats, each of these, you would say, like, if this is a chlorine, that would be the center, and then there'd be another cesium in front of it and behind it and above it and to the left and to the right. And so overall, the ratio is 1 to 1. So again, ionic compounds. Lattice points are made up of ions, positive, negative, positive, negative. And we should already know that it's an electrostatic attraction. And we should already know that these crystals can be hard, but they're brittle. So if you put enough force to break them, they don't smash, they don't flatten like a metal, they will just break apart into little bits. And they have high melting points. Meaning you have to get them really hot before they're going to liquefy, because these electrostatic attractions can be pretty strong. They are poor conductors of heat and electricity. So unlike metals that are also hard, they do not conduct very well. This is also going to miss not doing this one in class this year. Sodium acetate, they have this really neat crystallization that's exothermic. And so you can heat up you can dissolve a bunch of sodium and acetate and then heat it up and dissolve more to supersaturate it. And when it cools down, it'll be supersaturated. And so then if you poke it or stick your hand in it, it will quickly crystallize out. The sodium and acetate will form a crystal lattice, and it'll actually get hot. It's like hot ice. It's not ice, but it releases a lot of energy. You can grow lots. Industries grow crystals for all sorts of different uses. A lot of them for focusing light, used in focusing lasers. That's used in countless numbers of technologies. My son did a project. I think he got maybe for Christmas. I don't know. You can buy crystal growing kits, but really all you do is take a substance, supersaturate it, meaning dissolve a lot of it, as much as you can, in hot water, let the water cool down, and then let it sit for a couple weeks. And as the water evaporates, the particles will start sticking together, and you can grow fun crystals. Now, one neat application of certain types of crystals is that they are superconductive. Now, we know conductive means it can transfer energy, but anytime you transfer energy, there's typically a loss. There's inefficiencies. So it's kind of like if you think of a hair dryer or electric griddle, how they work is you run electricity through iron, and iron is a horribly inefficient electrical conductor. And so a lot of the energy gets converted to thermal or heat energy. So for wiring throughout houses and computers, we like things like copper because they have less resistance. Well, and so they don't heat up nearly as much. Though you've probably noticed your laptop or phone getting hot, and that's because of resistance. Well, a superconductor can transfer electricity with zero resistance. So it's like a perfect conductor. There's no energy loss. But there's a caveat. They only operate at really, really low temperatures. Now, there's a good handful of different semiconductors, but they all have to be like around 100 Kelvin. Some of the earliest ones had to be like less than 20 or 30 Kelvin, which were crazy low. So today we have warmer operating superconductors that can only have to be in like the 200 Kelvin. And that's good, but there's still challenges to bring that temperature up higher. One of the coolest applications of this is the Meissner effect. So if you can completely eliminate electrical resistance, then that material will no longer be susceptible to magnetic fields, or at least they can no longer penetrate it. And what happens with the Meissner effect is these superconductors kind of get locked in place at a fixed distance from an external magnetic field. And so here we have this superconductor that, again, it's going to pour liquid nitrogen on it, and this magnet is locked in place. So it's not, sort of attracted and repelled, but unlike a magnet that just would repel, it locks at this configuration. So you can move it with some external force, and then it just sticks. He's going to pull it up in just a minute. And what's going to happen now is it's going to warm up. And so as it warms up, when it goes above what's called the critical temperature, it's no longer superconductive and it falls off. This is, some people speculate, going to be part of a big wave of future train technology where you can have trains that are magnetically levitating using conductive material. We technically already have what are called the maglevs, but they use electromagnets instead. This is where we would watch some really cool videos about Lexus hoverboards, because in 2015, to go in line with the Back to the Future prediction that in 2015 we would have hoverboards, they made a hoverboard. And if you watch the videos, it looks super cool. There's a guy on a real hoverboard that is just kind of zipping around with no wheels, and he's like, always like 6 inches above the floor. He's just flying. What you don't know unless you watch the background videos is he's in a skate park that's been built specifically to have magnets pretty much lining the entire park, because you couldn't take the hoverboard to anywhere. It has to be over these strong magnetic fields, but still technically a hoverboard. The next type we have is the molecular crystal. Now, again, so this would be if you took something like dry ice, where here's carbon dioxide, normally a gas, but if you cool it down below 78 degrees below 0 in Celsius, then it will adopt a crystal lattice. Again, we've said before, molecules have the lowest of melting points, and this is because these crystals are held together by intermolecular forces, and they're significantly weaker than electrostatic and metallic and the other types of forces. So these molecules will be soft and have much lower melting points. Again, here's water and benzene. So again, 0, 6 degrees. Again, they melt very easily because the force between molecules is very, very weak, especially compared to the other types of crystal substances. So the lattice points are not ions, they're entire molecules. Now, sometimes you can have, and they're also poor conductors, sometimes you will see molecules as solids, and that's when you find the larger, again, it's dependent on size. Melting point goes up as the size and polarity go up. So take something like sugar, and it's a larger molecule, and it can form lots and lots and lots of hydrogen bonds. So table sugar, sucrose, doesn't melt to 180. Now that's still low compared to ionic and metallic substances, but it's higher than these ones. Again, and if you want to try a hand at crystallization, forming your own crystals, making rock candy is pretty simple. You can find some good online tutorials. It basically amounts to boiling a ton of sugar, getting as much sugar as you can dissolve in boiling water, and then letting it cool down. And you typically put like a tiny piece of sugar, like sugar crystals, like on a piece of wood or something, lay it in there, and then over time, as water evaporates, sugar will build a crystal lattice on top, and you can grow this delicious rock candy. Next, we have the covalent crystals. Now, this one is a little bit different because it's often confused with molecular crystals, because molecules have covalent bonds that hold each distinct molecule together. Covalent crystals have covalent bonds, except the difference is they're holding the lattice points together, where in molecular crystals it's intermolecular forces. So you could think of a covalent crystal as a huge, enormous molecule that just keeps repeating. Now, for all of these molecular, we can give a formula, H2O, C6H6, CO2, and those formulas tell us about some specific tiny molecule that can repeat over and over. But if we look up if we're talking about quartz, and we say, oh, it's silicon oxide, that's just the empirical formula. This thing can repeat over and over and over and over and over. So covalent bonds are holding silicon and oxygen together, but it just keeps on going. So again, think of it as a molecule that just doesn't stop. And so it grows bigger and bigger. So there's not a formula that we would give that would say a molecular formula. So when we say SiO2, that's again, empirical is just the base ratio. So the lattice points are going to be non-metals because those are the ones that covalently bond. They're held together by covalent bonds. And unlike molecules, these have high melting points. Again, down here, this is the crystal. This is what we're seeing. This is a diamond. So diamonds are really strong because they have this three-dimensional network where every carbon is forming 4 tetrahedral covalent bonds to 4 other carbons. And then those are forming tetrahedral bonds or to other carbons. And it just keeps going and going and going and going and going. So again, they're very different than molecules. Again, their properties change. Here's diamond versus graphite. Graphite has 2-dimensional sheets. Again, they're still considered covalent crystals, but the sheets are only held together by weak intermolecular forces. But generally, they all will have high melting points because you would have to put enough energy to overcome intramolecular, not intra. So these covalent bonds, which is much more difficult. And so they also don't, they have varying conductivity. It depends on a lot of different things. Like quartz is not super conductive, but diamonds are great thermal conductors. Graphite is a pretty decent electrical conductor. So it just kind of varies. Oh, and here, I guess I didn't take this thing out, but this is where we would watch a video. And you should watch these videos because, what else are you doing? Probably Minecraft. Lastly, we have metallic crystals. And this is probably the second one we've talked about the most, where metallic crystals, easily kind of straightforward. Lattice points are metals. We call the interaction metallic bonds. They have high melting points and they're hard. And unlike some of the other crystals that we said were hard and with high melting points, like ionic and covalent, these ones are good thermal and electrical conductors, and they are not brittle. They are malleable and ductile, so they are deformable. And this goes back to the whole electron C theory. So that being that their electrons are able to move about and they're delocalized. And so these bonds are non-specific. So if you push on some of these atoms and make them move, the other ones can move. They can adopt new configurations and be just as happy. Again, there are different allotropes of many metals. This one is a conversion of beta tin to alpha tin. So this was at low temperatures, but as it increases, we're going from one allotrope to another. And what's weird is, again, the density is changing, so you're seeing this thing expand. Mercury is a common solvent. Well, it's not super common, but a solvent for metallic crystals. So metals with their metallic bonds, again, since water doesn't have metallic bonds, it doesn't dissolve metals, but mercury has metallic bonds. And so if you want to break down a metal, here's what mercury can do to it. And for that reason, it's illegal to bring even small amounts of mercury on airplanes and, well, other places you would want to compromise the integrity of the metallic structure. And with that, we are done. So here you can read over a review. Here's some nice videos you should watch with all your extra time. And I wish you a very good